Similarly, bodies will also behave. There is going to be a reaction force where there is a constraint. If a body is allowed to rotate, no problem. If it is not allowed to rotate, then there is a constraint. So there is a moment reaction. Similarly, if a body is allowed to move in the horizontal direction, there is no constraint. But if you constrain the degree of freedom in the horizontal direction, there is a reaction in the horizontal direction. If you constrain the movement in the vertical direction, then there is a reaction in the vertical direction,
Okay, sir.
irrespective of the applied load, irrespective of what is happening. It might so happen that the value of the reaction force is 0 when you solve the problem based on what the applied load is. But when we are drawing the free body diagram, we should only look at the constraint, try to understand what degrees of freedom it is constraining, and accordingly draw the reaction forces.
Okay, sir. Got it.
Sir,
Yes.
sir,
Excuse me,
why
sir.
are we applying reactions only in the direction in which the motion is constant? Is it because of third law, Newton's third law of motion?
It is equal and opposite. Yes.
Sir,
Okay,
but
sir.
according to Newton's third law, hello?
Yes.
According to Newton's third law, a reaction will appear when we apply any force, external force. But here
The
in the
external force is the applied force on the structure.
who will applying, sir? Who is applying a external force?
When we are drawing the free body diagram, this is only a part of the structure.
Yes.
When you draw the entire free body diagram, there will be some applied loads also.
Sir, here body is not applying any force on the
This is
constraint.
no. I think you did not understand. So as I said, this is part of a structure. We are only focusing on the constant. This is part of a much bigger structure.
Yes, sir.
Yeah, the different roller supports that I have shown is part of a bigger structure. This is
Yes.
cut here. Maybe this was something else like that. We are only focusing on the constraints, trying to understand what the free body will be at the constraint. The applied load will come into the picture when we are looking at the entire body. Don't worry. Did you look at my presentation 2 and 3? Hello?
Yes, sir. Yes, sir.
So,
I have watched all the 3 videos and
so there now you should understand now that this is only a part. The force is applied. That will come later.
okay, sir.
Sir,
Excuse me, sir. Sir, there won't be any moment for this roller support.
No, because it is allowing rotation. If you have a support which does not allow rotation, then you have moments.
Okay.
Sir,
Sir,
is
if
the
the roller is
resultant or the reaction force
No,
Sir, your
if
screen is
the,
not
reaction
visible.
force
if the roller is, somebody was asking a question.
yes, sir. Sir, if the roller is moving in the x direction, sir, this implies if we detach the roller and the rod, sir, then if the roller is moving in x direction, so it must have some force in the x direction also, no?
That is the applied, na? That will be the applied.
Sir, so it will when we are detaching the rod, sir, then we'll have some force in x as well as y, na, sir, because
No, it is in a state of
if it is
static equilibrium. We are only imagining what the constraints are doing. It is not going to move because it is in a state of static equilibrium.
okay, okay, sir.
This is not dynamic
Sir.
equilibrium. We are not interested in dynamics at this point of time.
Okay, sir.
sir, in slide 14, can you please?
Slide 14 of what?
14. First, sir, equilibrium first.
Which we just discussed, yes?
Sir, it is written 3 force must be concurrent.
Yes.
But the condition should be also if any 2 of them are concurrent, then third must be concurrent.
No.
This
Three
will
of
be
them
a better point.
3 of them have to be
Two forces
concurrent.
to a
Sir,
same
if
point
The
can
two
never
force
be
will always be
concurrent.
concurrent.
2 force will always be
Two forces
concurrent.
will always
Yes,
be
sir. Because they will
what if
always
they are
have a
If
parallel?
they are parallel, then there will be no rotational equilibrium.
Ha, right.
Yes.
No, I have chosen a point which is in between them. Then it will be.
For
It will have
No,
equal
how
and
hard
planar,
force can give,
for a
hard
planar
force will
system,
give a
they will
torque
always
about
be.
that point.
I'm
One at a
asking,
time.
sir.
One at a time, please. Yes. Who was Karan? You were asking, is it?
Yes, sir. Suppose a rod has, I am, sir, taking middle point center of mass and two equal and opposite forces act at opposite end.
Huh?
And third force I apply at its center of mass, then it will be in equilibrium, sir.
No, why
But
should it?
three are
No,
not all concurrent.
no, it will not be in a state of equilibrium. Why should it be in equilibrium? We will come to that. The specific problem that you are talking about, we will discuss that. That is one of the slides that I have planned.
So in that case, resultant force will be 0, but moment will not be 0.
Correct. Yes. So it will not be in a state of
Yes,
equilibrium.
yes.
Okay.
Okay. So now what should we do?
So can you explain that the detachment case, the
Which
force
did,
in, so you told about one detached that in force like if it is detached it should have a force in x direction.
huh? Which one?
So now actually I could asked as a doubt that roller case.
Mm-hmm. Yes.
So in
What is
that
the?
so you told no suppose if it is detached then there should like you told there will not be a force in x direction. Can you explain the reason again?
Because constraint, there is no constraint in the x direction. In a constraint, you will have reactions only if a certain degree of freedom is constrained. If you are allowing a certain degree of forces, there cannot be a reaction force because you're already allowing that.
Oh, okay.
In this
So if the
roller,
reaction
vertical
force is
movement is
zero,
not allowed, horizontal movement is allowed. Since
Yes.
vertical movement is not allowed, you have a reaction in the vertical direction.
Direction. Okay.
And this freely guiding slot is a slightly different version of the roller support. In this, what happens is that you have a slot. This is a freely gliding slot. This green one, the green one that you know is called the freely gliding slot. It allows a movement of this member along the length, but not in the perpendicular direction. Like this green pin allows it to move like this, but does not allow this to move like this. So your reaction is only in the direction perpendicular. Okay? And all of this mean the same thing. All of this mean the freely guiding slot. Okay. Since there is limited time, I am jumping to the points where I have received most number of doubts. Okay. If there are some doubts which less people have asked, we will discuss that tomorrow. Okay. Because we only have 20 minutes left, there are some few conceptual things that I want to clear. The first one was about this. So this is a member A, B, C, and you have another member C, D. So A, B, C and CD are joined by a pin at C. So let us try it, and the applied load is 2.5 kilonewton at this point, and a moment is applied at point B, which is 4 kilonewton per meter. Now we want to draw the free body diagram of member CD. There is a pin at D, there is a pin at C. So in the pin, you know that the horizontal and vertical movements are constant. So you have a dx, dy, cx, cy. Yes?
Yes, sir.
Yes, sir.
Okay. Now I have dx, dy. Can I write the resultant of dx, dy? Both of them are acting at point D. So can I replace these two by a single force RD?
sir, I missed. What is which rod is this one?
We are looking at member CD.
CD. Acha, fine, sir.
Pin at C, pin at D. So I have put dx, dy, cx, cy. Now I am saying dx, dy acting at D. So let us have a resultant RD at this point. Similarly, I can have another resultant RC at this point. Yes or no?
Yes, sir.
Now this body, we are neglecting the mass. Now this body is subjected to only two forces, RC, RD. If a body is subjected to two
Excuse me,
forces,
sir.
yes,
So suppose I do not apply any force on the given body, then reaction will act on the constraint or not?
it will be zero. So the reactions will be zero.
Okay, sir.
Okay, so now a body CD is in a state of equilibrium. It is subjected to two forces RC, RD. What can you say about RC and RD?
Must be collinear.
Yes,
They must be equal,
In opposite direction.
Equal and opposite.
Equal and
must be
opposite.
equal, opposite, and
opposite.
equal and
DY
opposite is
and
not enough. It
DY
should be
should be
equal,
zero.
opposite,
Yes,
and
equal
collinear.
opposite.
Equal and
As well as
So if I'm saying RC and RD are collinear, what can I say about CY and DY?
They should be zero.
They should be
Zero. Zero.
Yes. So the free body diagram will actually look like this. When you have a body which is subjected to forces only at the tips, then the reaction forces must be equal, opposite, and collinear. Such members are known as two-force members. This is a very, very
Sir,
important
if
concept.
they are,
Please
sir-
let me complete. Let me complete one,
Yes.
please. This is a very, very important concept to master problem sheet number 4. And throughout the course, problem sheet number 4 is the easiest one. So if you don't understand this concept, then mechanics, I think it becomes very difficult to get good marks, because that is the topic where most of you are going to score. And that is entirely based on two force members. Okay. Yes, everybody understands why CD is a two force member, why CY is 0, why DY is 0, or should I explain again?
Sir, you explain again.
Explain again.
Explain again.
Sir,
Yes.
sir, if we know that CX and DX are equal and opposite, what is the need to write
yes,
CX and
sir.
DX?
Sir, if they are
Because-
equal and opposite, sir, they can give a couple force about the center of mass or about any point in the rod. So the
So
rod
it has-
must rotate.
So it must be collinear also, that's why.
No, sir, I'm not
CX and
asking
DX
what he asked.
should also be equal, no?
Yes, sir. CX, DX are equal, so we need
Why
not
we are
to write them.
writing
No. But then when you are drawing the free body diagram of member ABC, then at C in ABC will be equal and opposite to CX. You need to find that out.
Okay.
So then why we are doing CY equals to DY if CX is equals not equals to DX?
CX equal to DX. Who is saying CX is not? So CX and DX are equal in magnitude.
CY and DY?
CY and DY are necessarily have to be equal to 0 in this case.
So why we are applying them then? Like why we are not removing them?
Why are we not removing CX and DX? Is it?
Yes, sir.
That we will come to in the next slide. That's a very valid question, but let me come to that in the next slide. So everybody understands, yes, why CY and DY are 0 and why CX is equal to DX, yes or no?
Yes, sir.
Okay,
Yes,
now imagine
sir.
that you want to calculate the stresses at a point. Let us say if my body CD was deformable, then the value of CX equal to DX is important. I cannot wish it away. This is one reason. Then the other reason is, let us try to draw the free body diagram of member ABC.